When we are considering complex integrals, they are very similar to the ones we are used to in the real case. Also here we have some real variable t, and this variable t is the argument, and the function is a complex function of this real variable. So this complex function has some real part and some imaginary part. So for each value of t, this w of t is a complex number with real part u of t and imaginary part v of t. We can make the following definition of the derivative of w with respect to t. It's just the obvious definition like this, that we take the derivative of the real part plus I multiplied with the derivative of the imaginary part. Using this definition, it's really easy by using what we know from the real situation, real analysis, that the derivative of a constant multiplied with w, when we are taking the derivative of this with respect to t, this will be the same as taking the constant out of the differentiation sign like this. So the derivative of this function is equal to c multiplied with the derivative of w respect to t. So this is the case when c is a constant. If we say that t is bounded between some constants a and b, that we have some interval a and b, and that we want to consider the function w of t in this region, we can find the integral of the function w of t. And this is also a matter of definition. We just take the integral of the real part and add this to I multiplied with the integral of the imaginary part. We see from this that the real part of this integral is just the integral of the real part. This is easy to see from this definition. So taking the real, this real operator, we can put it inside the integral sign if we want. The same for the imaginary part. The imaginary value of the integral is equal to the integral of the imaginary value. Let's now find the following integral by this example. In this example, we let a and b be equal to 0 and 1, and let w of t be equal to this integrand. So using we now recall the definition of this integral. We should integrate the real part of w of t, which is we call u, and we should add this to I multiplied with the imaginary part v of t, the integral of this. So first we have to find this u and v. So this is really easy to do. We just compute it directly and find that u of t is equal to 1 minus t square, and the imaginary part is equal to 2t. So now we can integrate u of t and v of t. U of t is this. It's easy to find the antiderivative of 1, for example, it's t. The antiderivative of t square is 1/3 t to the power of 3, which we have here. And we have to use these limits 0 and 1. They should be eventually inserted into this expression. And the same for this imaginary part. The antiderivative of 2t is, of course, t square. So inserting these limits, we obtain that the integral we are searching for has a real part 2/3 and the imaginary part equal to 1. So this will be then the complex number corresponding to this integral. Well, we could have used a much simpler method to find this integral. In fact, we are not going to prove it, but it's possible to show that finding this integral from a to b is just the same as first finding the antiderivative of this function and insert these two limits. So we take the antiderivative of the function and insert b minus the antiderivative of the first limit point a, exactly as in the real case. So this often is a much simpler method. We also want to emphasize that it's possible to divide the integral from a to b into two or more integrals. For example, if we want to integrate from a to c first and then from c to b, then we can add these two integrals and the resulting integral turns out to be the same as the integral from a to b. This is a useful method, especially when the function w of t is described piecewisely. For example, we have one description of the function from a to c and another from c to b. Then we can divide this integral into two parts, or more parts if we need that. Let us use the method of which we talked about, this method for finding the integral from a to b, namely by finding the antiderivative directly. Let's take this example where the integrand is this exponential function of it, and the antiderivative of this is, of course, this expression. Just take the derivative of this, you will immediately see that we obtain this integrand. So inserting the limits 0 and p12, we obtain this expression. And noting or recalling that the exponential function of some angle multiplied with some real angle multiplied with I is equal to cosine to this angle plus I sine to this angle. We obtain this. Here we also recall the table values presented to you before, that the cosine of 45 degrees is the square root of 2 over 2, and the same for the sine value. So we directly obtain, using that, yes, here we should multiply both the numerator and denominator with I, and then we see that we use or observe this identity, and this is used to obtain the resulting integral. Real part is the square root of 2 over 2, and the imaginary part is 1 minus the square root of 2 over 2. Let us mention some important properties of the integration. Here you see a typical integrand w of t in the real case, and you see that when taking the integral from a to b, we can illustrate this in some sense by observing that this integral is the same as the area under between the horizontal axis and the curve. When it's above the curve, we get a positive integral, but when it's below the curve, we get the negative value of this area. So this is rather general, and we see that taking the absolute value of a function would increase the value of the integral. So increase or let it be exactly the same value. So the absolute value of the integral is always less or equal to the integral of the absolute value. So this is an important inequality which we will use later on.